This is the last session of this morning, so Samuel Brevitt, Singularity of Lévy works in the lifted Pomeau-Manneville map. Thank you.
Thank you. Can everyone hear me okay? Okay, brilliant. This is based on joint work with several other people, among whom Rainer is with us today and will be speaking tomorrow, although not on this subject. Some of you may have seen before, some of you may not. This is work on the Pomeau-Manneville map, which is a very classical example of an intermittent map. This is work in deterministic dynamics, so this is maybe a bit different to some of the other stuff that you'll see. This map is defined on the unit interval, and we are simply taking some initial condition, and then after one time step, xn plus 1 is exactly this function of xn. This map has a marginal fixed point at 0, marginally unstable in the sense that the gradient at 0 is exactly equal to 1. And so what makes this map interesting, it's expanding everywhere else. So generally speaking, you're getting a sort of chaotic behavior, but then this marginal fixed point has a kind of trapping. The idea is that it kind of traps points close to it for a long time, and so you get this intermittent behavior of long periods of kind of laminar motion and then short bursts of chaos. This has been well studied since the late 70s. A lot of work done in the 80s and in the 90s. What we can do with this is we are lifting this then to a diffusive map along the real line. There are various ways of doing this, and we've chosen to do this in such a way that the marginal point is now mapped to the edge of these branches. It's kind of maybe not so clear to see. And the idea is that by doing this, firstly, the branches overlap, you generate diffusion. You may have seen diffusion like this generated by piecewise linear maps that are constructed similarly. But in a particularly special case, you'll see in this illustration here, if you follow where the edge of this branch maps, it maps exactly onto the same point in the next branch over where the marginal point is. And so if taken on the unit interval, this kind of traps points here. In this case, it moves points along up and down the line for extended periods of time. And so we're in that special case where that mapping is exact. It's long known that this can produce superdiffusion. So based on the parameters of the map, there's a parameter z which controls the kind of strength of the fixed point. As you transition through different phases of z, there's a regime where it's basically normal. Diffusion is normal diffusion. Then you get this kind of super diffusion with a propagator that is not Gaussian. And then there's a third regime where it's we call it ballistic motion, where most trajectories are moving in one way or the other, and there's this kind of propagating front in the density. But so in this case, where the height, if you like, of these branches is exactly 1, this was long known to be approximated by a Lévy walk, or a continuous time random walk, where to put it very briefly, I haven't written this on the slide. We are starting at the origin. At every what we do is we pick a direction. I'm only considering in one dimension here, so we pick left or right at random, and we move at a constant speed in that direction for some length of time. And that length of time is going to be drawn from this distribution, which it turns out to be is a power law. The power law the fact that this is a power law is what defines this as a Lévy walk, effectively. And then, so we move in that direction for that length of time, and then again, pick left or right randomly, move, draw independently a new flight time. And so there's a sort of classical argument you can make based on how points escape from the the marginal point of the Pomeau-Manneville map that justifies from sort of first principles, although not exactly, making some nice approximations as to why you can model this as this, and then you can from that calculate this very nice theory around continuous time random walks. You can get expressions for the mean square displacement. And again, it goes through these three regimes on the basis of the parameter. And so you can see there we have the normal diffusion, and then we have the super diffusive and the sort of ballistic regimes appearing in this. The reason I discuss all of this is that this is where the literature kind of stops. But this is not the map and the Lévy walk are not the same thing, and they behave a little bit differently. So I'm going to show investigations basically coming in two parts. Firstly, under varying the two parameters of the map, essentially. Firstly, the height of the branches, which we've labeled here as R, and secondly, the strength of the fixed point, the strength of the nonlinearity, which we're calling Z. And on the variation of these, we'll see that the situation in the map is a bit more subtle than in the Lévy walk. When we vary the height of the map, there are a few observations. Some of them are a bit trivial, and some of them are not trivial at all. What I'm showing here are plots, three plots for the three different dynamical regimes, varying along the x-axis, the horizontal axis, the height of the map R, and on the vertical axis, this exponent in the mean square displacement, this beta. And what you can see in the dotted red line, the dashed red lines, is effectively the prediction from the CTRW that this exponent is 1 in some regime, then it increases, and then it's 2 in the ballistic regime. And what you can see from the blue points are generated from simulations. I won't go into too much detail about how the numerics of how that's extracted, but it's very, very good. Very good results. You can see, certainly in the last two cases, that in isolated points, we do get the super diffusion that is predicted. Exactly when the height is equal to an integer, because that's exactly when the fixed points all lined up. That's a fairly trivial observation, I think, but it is worth noting because, it is only at exact points. Outside of that, you typically get normal diffusion, because if the fixed points are not mapping, then any higher iterates of your map are expanding everywhere. But there are certain things that are a bit less obvious, which is that there are certain regions where the diffusion is suppressed completely. When R is less than a half, it's always suppressed completely because the branches don't overlap enough for it to diffuse. But also, for R slightly greater than the integer, so we see that, and you can, on each of these plots, there's a kind of zoomed in region where you can see this a bit more clearly. When R is slightly greater than an integer, diffusion is suppressed completely. And the reason for that, if I show on the plot on the left here, is that so the green lines here are showing sort of trajectories, if you like. Is that it instead of mapping exactly onto the fixed point of the next branch, I kind of slightly overshoot, and I instead get mapped to the returning branch. And so if I start at 0, I move up to something slightly greater than 1, and then I move back down to near 0 again. So there's this kind of if the height is just slightly too big, then this actually completely contains, it isolates the dynamics. In the right-hand plot here, I'm showing the case where R is quite small, and you'll see that you sort of get these isolated islands because the branches don't overlap enough. But the dynamics of what goes on inside these islands are also quite interesting, because they form their own little closed systems. And actually, there's a very interesting structure that emerges here. there's a bit too much information on this slide, so let's go through this fairly slowly. If I look just at these little islands and I look at the map of mod 1, so just focusing right in on that region, on the leftmost plot here, I'm showing bifurcation diagrams, effectively showing the stable regions, or the regions that can be occupied by the dynamics. And you see that okay, when r is greater than a half, everything is filled because the thing just diffuses everywhere. When r is less than a half, it's separated off into these boxes, and the sizes of these boxes depend on the height of the branches. But there's these little bubbles that emerge here, and you can kind of see that a bit actually on the previous plot here, right? Where this looks like it's an individual periodic trajectory. It's not. This is actually a kind of group of trajectories, a sort of stable region, and you can see there's these little bubbles that emerge. And this basically turns out to be, if you look at higher iterates of the map, you can identify stable and unstable periodic points, periodic orbits. And so these bubbles became quite interesting. You can see it in the z equals 1 case, which is actually just the piecewise linear map. When z equals 1, the whole thing reduces to a piecewise linear map. And so it's kind of surprising that this has not been, at least not to the knowledge of any of the authors, that this has not been seen before. But also in z equals 2, you get a similar thing, but it's a bit more interesting because, again, when r passes 1, there's this kind of, at r equals 1, everything goes to the fixed points because that's when you have the superdiffusion, and then the same thing occurs again, except there's this crisis point where the null diffusion kicks back in again. And so on the latter two charts here, I'm showing the same thing. It's zoomed in a bit closer, so you can see these bubbles, and you can even see that there are bubbles almost kind of within bubbles, and we think, you can take this to more depth as much as your numerics will allow, and we think there is an infinite cascade of, as you approach 0, a very interesting bifurcation structure that, that as far as we're aware, has not been looked at before. And actually, these boundaries of these stable regions can be calculated analytically, at least for the first couple of iterations. Obviously, the crunching numbers gets a bit harder the deeper down you go. And running right through the middle in red here is an unstable periodic point. And so the three of them will meet at this crisis point, and that's going to be the same for each of the bubbles all the way down. So, a very interesting structure. I've not got much time left. I said I'd keep things brief because lunch is approaching. But the second thing we want to look at is the variation of the z, the nonlinearity of the map. So for everything from here on out, I'm going to fix r equal to 1. I'm going to fix the height of the map so that we have that exact superdiffusive behavior, and I'm just going to look at the nature of that superdiffusion. So we have our three regimes then, where we have different values of beta, as was prescribed by the by what we've seen so far. And what I'm looking at here now on the vertical axis is the prefactor in front of that, right? The constant in front of the t to the beta, which is a generalized diffusion coefficient, effectively. This is not the same as a diffusion coefficient as you might see with in physics, because it differs by a factor of 2 in how it's defined. Typically, you'd have a 2 on the bottom here when you're defining like a diffusion for a Brownian motion. But okay, it is what it is. And so there's this nice shape that's prescribed by the calculations, by the stochastic calculations, and we match that pretty well in simulations all across the board. There's this peak and there's this trough where you have at the transition points, because you have these logarithmic corrections, but as you increase your simulation times, you get closer to it, everything looks really nice. But then there's this thing that happens at z in the limit as z goes to 1. Where the the Lévy walk theory says we should get k exactly equal to 1, and we don't. We get k equals to 2/3. And actually, because z equals 1 is the piecewise linear case, you can analyze this by other methods, and they agree it should be 2/3 quite easily, quite standardly. So there is some mismatch here, and this again, we don't think has been addressed at all. There's literature that compares the map and the CTRW, and it's not been noticed to our knowledge. There's this discrepancy. So we tried to look at this a little bit. I mean, we have sort of partial explanations for this in the red plot up here. I don't really have time to go into what I mean by TGK. TGK here is Taylor Green Kubo, but it's a sort of a way of expanding, a way of doing the numerics that sort of separates the thing out into varying degrees of correlations, of autocorrelations. And so what we see in this transition from z equals 1 to the to 3/2, where the first real transition point appears, correlations become more and more important, correlations between time steps. There's also in the blue plot here, this is a bit, there's more going on here, but a discrepancy in the limit between the density, between turning points of the map, between what's predicted by what's used in the CTRW and what's used in the Pomeau-Manneville map. Now, of course, you could say, well, why don't we just change the density that we use for the CTRW? Well, in a sort of asymptotic limit, this works just fine. But then there's some kind of, something that goes wrong that just gets bigger and bigger in the Z-1 limit. I'm going to wrap up there. We did, just to very briefly, we looked at aging because this thing is because of the super-diffusion, this thing has dynamical aging, and this actually, as you increase the aging time or the ratio of aging time to measurement time, this actually kills one of the not a singularity, but this trough here in the prefactor. This is also predicted by CTRW. You can use certain techniques, and it was used to analytically see that also. But it's worth noting that that is also observed in the simulations. And that's all I have to say on the matter.
Question or comment?
Yeah, please.
Do you think that the trough would be observed if you kept pushing the simulations?
The trough would be observed.
The trough on the Lévy process. Would you see, or the peak? Do you think you'd have a peak more like that?
In the aging or in the non-aging?
The non-aging.
So in the non-aging here.
If I'm correct in assuming that the higher the t, the closer you're getting to what you're trying to find. If that's wrong, then what I'm saying could be nonsense.
Yeah, no, that's the idea. The higher the t here corresponds effectively to measurement time. The higher the t, the better results we're getting. And what we see here is exactly that, right? As we increase the t, we're getting deeper and deeper. Now, whether this goes all the way, I mean, it can never go sort of exactly all the way because finite measurement time and things. But that's effectively what we would expect. And with the shape of these results as it stands, I'm satisfied that that would be the case. With more detail, you could look into that more deeply if you wanted. When the aging case, that kind of conflicts because then as you increase the aging time, you actually get further away from that. So I think the general understanding here is that the relevant factor is actually the ratio of measurement time to aging time. and everything else sort of follows from that.
So this problem is that these transitions are marked by logarithmic corrections, and that makes it hard in the simulations to observe that. So these are kind of dynamical phase transitions, and this seems to be generic. So whenever you have transitions in stochastic systems between different regimes of diffusion, meaning crossover from subdiffusion to normal diffusion to superdiffusion, it seems that generically these transitions are marked by the existence of logarithmic corrections. And again, I mean, this causes trouble, and that explains exactly why you have the slow convergence. So this seems to be a generic problem. Also in experiments, if you would do real experiments. Which is interesting.
I think where did this show? Yeah, I showed.
Yeah,
so on this slide here, this is the one.
Yeah.
Your mean square displacement goes at this exact point. It goes as t log t. So in principle, if you were to divide through by, there isn't really an appropriate beta in this case, but that's where that comes from.
Any more questions? All hungry? Okay, thanks again, speaker.